All right, welcome to CS4510. This is L08B. This is the second half of the lecture we just did on Turing machines. And the topic of today is why is the Turing machine definition a good one? That's sort of what we're focusing on. Half of this was my faculty interview, so that that's sort of where this came from. I made this content really to get hired. So let's kind of talk about where we are in the course. We talked about DFAs. They didn't really work as a model of computation. We immediately found problems they couldn't solve. We talked about NFAs. Nothing happened with them. They're the same. We talked about PDAs. Again, more complicated argument, but pumping, we were able to find languages they also could not do. Let's go the other way. Instead of taking something and then appending stuff to it, hopefully to get a larger and larger class, let's just go the other way. Try to find something that's as powerful as possible and then argue about that. It turns out that's all really the Turing machine is. So let's go back again and review quickly what the definition of a Turing machine is. Here's one definition. Let's suppose we're using a computing definition. We have some finite set of states and we have a finite tape alphabet. Let's just suppose it's 0, 1 with a blank. And here's our transition function. You read a symbol off the tape, you write a symbol, and then you move left and right. And as you do so, you transition between the states here. So the diagram is much more informative, of course, than the formal definition. You start somewhere and then you stop somewhere, right? As you do so, you iterate over this tape and you read and write symbols to it, right? One at a time in some very small, minute mechanical process. Shield your eyes. This is what computer science used to look like when we left it in charge of mathematicians. Don't read these too carefully, but I just want to tell you these are two screenshots from two proofs that we can now do much simpler, but back in the day, they didn't really have good tools to do it. So the first one is a lemma from a book by Martin Davis. And we don't even need this lemma anymore because we can basically do it the proof has been simplified through the use of a Turing machine without having to do any of this nonsense. The second one here is from a screenshot from a paper by Alonzo Church, which is considered the first paper in computer science. He defined the lambda calculus, and he talked about, it turns out we'll later see its equivalence to Turing machines. But he says for a set of recursive equations consisting of the recursive equations of f together with these equations, and he says, for example, I1 of 2 is equal to 2, and the successor of x of 2 is equal to 1, some things like this. And essentially, what he's doing here, and he doesn't even realize it, but he's using we don't need to do any of this stuff with functions anymore. Today, we would call this an instruction set. He's creating a set of very minimal operations, but he doesn't know what an instruction set is. He doesn't know what a computer is because the computer hasn't been invented yet. He's a mathematician. He's a classical number theorist training. So he's doing it this way without knowing that today we would call this later an instruction set. Second thing I'll say about this is he did not, being a number theorist, recognize 0 as a natural number. This class, of course, we do. So while we use 0 and 1, Boolean logic is just built into us as doing majors. He did not know this. So he used 1 for true and 2 for false. So 1 and 2 here are meant to be analogously 0 and 1 as we would do it today. So he did all the math with 1 and 2. Today we would do it with 0 and 1. Again, the problem with both of these things is, that we don't even need to read this, it's complicated, is that these mathematicians are working with functions. What is a function? A function takes the input and it gives you the output. It's an association. That's it. It's a relation. Nothing else. But that's not what computation is. And computation is inherently a mechanical process. It's physical. It's built upon sequences of atomic steps. And it is not a function. So coming with the perspective of a function is a really bad first start. These are some examples of devices that existed in Alan Turing's time. And they all kind of worked procedurally. Here's some mechanical calculators, a typewriter. This, obviously, you can see the influence of a Turing machine because it has a tape there that it punches holes in. Now, this is a writing, it can't read, but it can write to such a tape, right? This is much older. This is like from 1600s or something. This is by Blaise Pascal. And I think it's a mechanical adder. This whole device is intended to carry the bit operations. And we did create a Turing machine that carried the bit forward. I believe this is such a device, but maybe in base 10 or something, right? So computation is mechanical. It's procedural. It proceeds as a sequence of atomic steps. It's never a function. And really, the first person to realize this was Alan Turing, above anyone else. And here's a photo of him in high school or something like this. Here is a letter I found. I was digging in the Alan Turing archives looking for some kind of mechanical devices that existed during Alan Turing's time, and I found this letter he wrote to his parents when he was 9 years old. They sent him to boarding school, British, etc., etc. So it is luck I don't have to show up my letters, or Mr. Darlington would confiscate the whole bottle, probably. This week I thought of how I might make a typewriter like this. And then here's perhaps a typewriter head that is in a tree instead of maybe a line or something, so it's some kind of spirally typewriter head. Here's another one he's crossed out, right? You see the funny little rounds or letters cut out on one side along to the round A, and along an ink and had stamped down and make the letter. That's not nearly all, though, from Alan. So first off, what we see here is that Alan Turing is not a mathematician. He's probably the most successful mathematicians of all time, and we'll talk extensively about him. But he really was an engineering student before he was a mathematician. He has the engineering brain, as many tech students do, in the sense that you take apart your father's microwave and you fail to put it back together. So you look at parts and you look inside of stuff and you're entwined by these gears and levers and pulleys and whatever's going on over there, you know. His version of the microwave, though, would be, you know, a typewriter. He would be one of those YouTubers that would take apart the microwave and build a, whatever. You know what I mean? You know, everyone knows what I'm talking about, right? They're putting styrofoam in the microwave, part 30, you know, stuff like this. He's ahead of the game on this, but you clearly see he's not a mathematician. Mathematicians only know what they know. They don't know anything else. So it takes someone that's not a mathematician to invent something that they had never conceived of. But what did mathematicians know? Functions, numbers, triangles, that's it. And if you don't know one of those three, if it's not one of those three objects, then sets were relatively new in his time. So he came in to really define the idea of computation better than anyone else. And that's basically what the rest of the talk is about. So what is the Church-Turing thesis? Algorithm. What is an algorithm? What is the word algorithm is named after? Is algorithmy, which is a mistranslation of al-Khwarizmi, which was this, the guy, is Arab who invented multiplication algorithms and so on. The notion of algorithm is ancient. Euclid had an algorithm for finding GCD. There was algorithms the Hindus had for making calculators to determine positions of the moon, right? You can do Chinese remainder theorem to find, you know, solutions to, you know, market pricing and so on. So there was, Persians had algorithm to compute rates of interest. Everyone had algorithms because algorithms were necessary. Algorithm is just procedures. It's just things you do as a sequence of steps. A recipe, every cooking recipe is an algorithm. It's to make a peanut butter jelly sandwich is an algorithm, right? So we had, for ancient times, had algorithms. Most of the algorithms we've concerned ourselves with have been numerical because we're concerned with calculation. And the concept of a number is one that's pretty universal culturally. So, but algorithm is a very ancient task, but it's not a formal one. It's an intuitive one. Like, that's an algorithm. Okay, fine. You know, like, how do we formalize that concept? In the sense that what formally is an algorithm, in the sense that it exists relative to some set of axioms. So, the Turing machine, that's what the Church-Turing thesis says. If you have an intuitive algorithm, you have a corresponding formal Turing machine for every possible intuitive algorithm. The Church-Turing thesis asserts the Turing machine captures this intuitive definition, that everything computable in the intuitive sense is computable by a Turing machine. But why? Let me, again, reemphasize what the problem is that we're asking here. You deal with numbers, but numbers don't exist. Numbers are abstractions you use to reason about quantity. You can never have three. You can have 3 hats, or 3 dogs, or 3 hot dogs, or any 3 of anything. But you can never have a 3 by itself. 3 is an abstraction. It's an idea we use to reason about quantity. So the intuitive notion of quantity can be formalized as a formal definition of numbers. And then operations on quantity, such as addition and multiplication, can be formalized as operations on these numbers. But again, numbers aren't real. The Turing machine is a formalization of the intuitive concept. That's all we're saying here. But why is that true? The Turing machine is really simple. The Turing machine only has a read, write, and move. Why is it the case that everything that can be computed in a human sense, in the intuitive sense, is captured by this definition? Why is that the case? That's kind of what the rest of today is going to be spent on. So let's look at some wrong answers first. Here is the definition of the Church-Turing thesis from technically the official book for our class, Mike Sipser's Introduction to the Theory of Computation. A great book, but let's read his definition. Informally speaking, an algorithm is a collection of simple instructions for carrying out some task. Commonplace in everyday life, algorithms sometimes are called procedures or recipes. Even though algorithms have had a long history in mathematics, The notion of algorithm itself was not defined precisely until the 20th century. Before that, mathematicians had an intuitive notion of what algorithms were and relied upon that notion when using and describing them. But that intuitive notion was insufficient for gaining a deeper understanding of algorithms. The definition came in the 1936 papers of Alonzo Church and Alan Turing. Church used a notational system called the lambda calculus to define algorithms. Turing did it with his machines. These two definitions were shown to be equivalent. This connection between the informal notion of algorithm and their precise definition has become to be called the Church-Turing thesis. So this is Sipser's definition of the Church-Turing thesis. There's a bug in it. What's the problem with this definition? This is a philosophical question and not a formal one. We're working in pre-science here and not science, but there's a problem here. Yeah.
What was the question?
There's a problem here. His explanation is insufficient. Why? It's very subtle. It's almost like a trick of the light. I'll tell you. We are concerning ourselves with the equivalent of the intuitive notion of algorithm, right? And we're concerning ourselves with an intuitive notion and a formal notion. An informal definition and its correspondence with a formal one. We want to show those to be equivalent. He's saying that the equivalence between a formal notion, the lambda calculus, and a formal notion, the Turing machine, the fact that those are equivalent implies that the Turing machine is equivalent to the intuitive notion. So it's as if you prove DFAs is equal to NFAs, because DFAs and NFAs are both formal notions. The equivalence of those somehow implies something about a correspondence with an intuitive notion. But that's not the case, necessarily, right? Why does that imply that anything that can be done in a human sense can be done by a Turing machine? It doesn't. It just says that those two notions are equivalent. But it doesn't really say that the Turing machine is a good model of computation. Because it could be the case that both the Turing machine and the lambda calculator are both bad models. That's not eliminated by this explanation, right? Let's look at another explanation. This is from Hopcroft, Motawani, and Ullman. Interestingly, all the serious proposals for a model of computation have the same power. That is, they compute the same functions or recognize the same languages. The unprovable assumption that any general way to compute will allow us to compute only the partial recursive functions, or equivalently known as what Turing machines or modern-day computers can compute, is known as Church's hypothesis, after the logician Alonzo Church, or the Church-Turing thesis. Again, an insufficient explanation from a similar automata book, which is also as popular, or maybe less so, than the Sipser book for classes like this around the world. So again, we're like, okay, these things are equivalent to each other. But that still doesn't tell us the correspondence between the intuitive notion. Turing machine, again, 3 instructions, that's it. Why is it the case it can do anything, you know? We go to this book by Martin Davis, which is 1958. It's one of the first books in this field. The situation is quite analogous to that met whenever one attempts to replace a vague concept having a powerful intuitive appeal with an exact mathematical substitute. An obvious example is the area under a curve. In such a case, it is of course pointless to demand a mathematical proof of the equivalence of the two concepts. The very vagueness of the intuitive concept precludes this. Again, Turing machine exists in a formal system. You could prove things about it. The intuitive notion of algorithm, which we're trying to show the correspondence to, exists outside of the system. It's pre-scientific. Because of that, what Martin Davis is saying here is you can never formally prove the equivalence of such two because one exists completely external. It can never be formally defined because then it's just a formal definition. So the equivalence can never be mathematically proven. And we're given analogy towards why this is the case. You know, there is the integral is a very formal thing. It's meaningless, though. It's just a manipulation of symbols. But it has a correspondence with an intuitive notion, which is area under a curve, right? It's not defined to be the area under a curve. That's the intuitive, right? But again, we don't know why the Turing machine is equivalent to anything that a human can do in a computing sense. We still don't know that it's a good definition. So let's look at one more book, and this is the Lewis and Papadimitriou book. By the way, I think Papadimitriou has written like 7 textbooks on theoretical computer science. So here's his first thing. Here's how he proves the Turing machine, the power of the Turing machine. And in fact, this is a common strategy from other books, and we'll outline this strategy. Turing machines can be imitated by grammars, which can be imitated by the mu recursive functions, which can be imitated by Turing machines. The only possible conclusion is that all these approaches to the idea of computation are equivalent. This is Church's thesis, extended out to methods quite different from those in the theory of automata. To use our notation, we may simulate a Turing machine on these things we'll later call our universal grammars, unrestricted grammars. They're much more general than context-free grammars. But in fact, you can prove that a Turing machine can be simulated on an unrestricted grammar. You could also prove that such a thing can be simulated on this class of functions. And then you could prove the class of functions can be simulated by Turing machines. So because the Turing machines are on the left and the Turing machines on the right, all of these must be equal to each other, right? So in fact, all these are equal to each other. But again, the fact that all these interesting models of computation are equivalent to each other doesn't tell us that any of them are powerful. So here's the problem. Church's thesis that everyone is saying is like, okay, these are equivalent to each other. Let an arrow represent a simulation, provably so. These are all formal notions. We're not going to get into what these are. Lambda calculus, the Turing machine, a semi-through system is really a string rewriting system, and a cleaner Herbrand and Gödel recursive functions. Whatever, fine. We're not going to get formally about them. But know that these are all equivalent to each other because there exist proofs that show simulation one way and the other. These are all the same. But the question that's not answered by any of these is why is this analogous at all or equivalent to anything that's possible with a human? Why are any of these a good definition? You know, that's the problem we want to solve. And I basically spent like a year searching for this question, going through several books, trying to figure out, okay, well, this didn't really answer my question, let's go to the next book. This didn't really answer my question, let's go to the next book. Apparently everyone already knew the answer to this question, which is why it's not addressed. Because I should have really gone to the source to begin with, which was Alan Turing. Alan Turing defined the Turing machine, but in his definition of the Turing machine, he also gave an incredibly rigorous approach to why the Turing machine is a good model of computation. And here he is at Princeton, early 20s, right? So he solved an incredibly hard open problem that we'll talk about later called the Unscheidungs problem. So he wrote this paper on computable numbers with an application to the Unscheidungs problem. It's a classic paper now. But he defines a Turing machine. He gives several examples of programming Turing machine. For example, a Turing machine that takes no inputs and prints the digits of E and pi. Something like this. Just show that like common classical things can be done with a Turing machine. Multiplications, additions, and basic arithmetic operations. But besides these, to convince people that the Turing machine, he needs to convince people that the Turing machine is a good formal definition of computation, right? The guy who invented the PDA is not going to give a good definition of computation because we know there are immediately, by pumping arguments, there are things that can be pumped that are not context-free. So that's not a good model of computation. But he gives an incredibly rigorous argument. It cannot be a mathematical proof, but it's as close to a proof as we have to why the Turing machine is a great model of computation. And it's called the direct appeal to intuition. So that's the rest of the lecture is going to be basically outlining his direct appeal to intuition. So we can break this up into 2 parts. The Turing machines are equivalent in power to the human mind, at least with respect to computation. Now, of course, there's a lot of complexity and confusion in there, but we're only putting this framework with respect to computation. And the second point is there is no computing device strictly more powerful than the human mind. This is something that may be obvious, but it's worth a sentence or two. It's more of a postmodern perspective. So in some sense, we want to show this, right? Let L human be the class of languages decidable by a human that, that's it. Like there exists a human to solve a problem, right? This is a very large and robust class. This is huge. This is like anything you can reasonably think about has to go in here, right? In fact, it's not even obvious if there's anything not in here, right? We want to show that this is equivalent to LTM. Now, that's formal. This is informal. So the arguments will be somewhat informal when arguing about this. And by necessity, they must be. But we're still going to prove it, right? How do you prove 2 sets are equal? Double set containment. Let's do the easier way first. Why is it the case? Let's do this one first. L human is a subset of LTM? No, that's the hard way. Let's do the easy way. LTM is a subset of L human. Let's hear some ideas. This one's the easy one. Why is LTM a subset of L human?
Because it was made by a human, the Turing machine was.
I want more. Say more, yeah.
Because we can we can create Turing machines and we understand how they work and can explain them.
I mean, and that's close. So, inventing Turing machines and explaining Turing machines is analogous to what I want to say, which is that you can simulate the Turing machine. Here's the algorithm on a human. You let there be a Turing machine for some problem. We give an analogous human to do it. The human is going to look at the Turing machine, look at the word, just apply the transition function until it's like, oh, the machine accepted, so then I'm going to say yeah, right? The reason that works is because you can simulate the Turing machine, I don't know how, but on the neurons and pipes and wires in the brain, and somehow that allows you to get the answer the Turing machine was supposed to get, right? So, but when does this work? We'll define something called the fathomability criterion. Let C be any computational model, a decision procedure, or mechanical process. This is a vague and vague definition on purpose because computation is incredibly general, right? Chemistry could be computing, right, in some sense. C is said to be fathomable if you can think about it. Now, can we make that definition more precise? No. But you know when you can think about it, and you know when you can't think about it. Well, do you know when you can't think about it? Maybe not. But you know when you can, at least, right? So you know if something passes the fathomability criterion. So if C is any device which passes the fathomability criterion, then it must be the case that L of C is a subset of L of human. Now, why is that true? Because you can think about it. So why is the Turing machine LTM a subset of L human? Because you can think about it. Just think about the Turing machine, you think about the intermediary steps. Every time the Turing machine makes a step, so will you. Done. So we've done one set. And that kind of re-emphasizes why this is such a large and general class. I mean, obviously, any machine really is a subset of it. Because every machine we've had so far really passes this fathomability criteria. The same is true for DFAs, NFAs, PDAs, every context-free grammars. All that can just kind of, that works for free because you can think about them. Their intermediary computation steps all work out. Determinism or non-determinism. So let's do the harder direction. This is, in some sense, the explication. This is the part where we turn the intuitive concept into the formal notion. This is really the question we have. The reverse one comes for free. Why is this one true? Why is it the case that the human, anything that a human can do in a computational sense can be done by a Turing machine? That's really the problem Alan Turing solved, right? So here is the outline of the argument. And a philosophical argument is not too unlike a proof, but it of course can never be existing, fully formalized within a formal system. But here's his direct appeal to intuition. First, we agree on a computer, a general example of something, not in a physical sense a computer, as in your laptop, but an object possessing the action of computation. We can agree that's the computer, okay? Then, we slowly distill the example, making it more and more formal, removing more complex portions and simplifying it. And as we repeatedly make these steps, we must convince ourselves that it is in the act of computation, these changes are invariant to the act of computation. So that computation, the fact that this is a computer, is never perturbed. So that it's still a computer, we change it, that's still a computer, we're gonna change it, that's still a computer, we're gonna change it. And at the end, we should be left with a formal notion. And at each step, we repeatedly remove, we replace portions, informal portions with formal portions. And eventually, you ship a thesis, you get the formal notion out. And you'll be left with the convincing argument that you have a formal notion, which is satisfactory to the definition of computation, because the informal notion you agreed was the definition of computation. We must then agree that the composition of such changes will be correct. Okay, that's the outline of the argument. So step one, we need a computer. Where are we going to find one?
Like the idea of a computer?
Yeah, what is a general idea of a computer? Suggest to me something that is a computer.
Something that takes an input and outputs some form of output.
Okay. But the DFA is such a definition, perhaps. But we know the DFA is not that good of a definition of a computer. I mean, it is a computer and it's weak on purpose. But we want a strong and general computer. So suggest to me a very strong and general model of computation. Yeah.
Something that computes.
Okay, like what? We need an exact object. We're going to do some science.
uses numbers
Okay,
to compute.
okay. I need something more precise.
A Turing machine?
Turing machine, that's what we want to prove.
Okay.
So it needs to be, in the intuitive sense, something that's satisfactory to the definition of computation.
Something with the ability to
Compute.
read memory, write
Okay.
memory, perform mathematical operations.
Okay, those are good requirements, but what is something that can do that?
Calculator.
Calculator, there are some things the calculator can't do. Add 31-bit numbers, 33-bit numbers, sorry. Okay.
I will probably steer this off, but what about set theory?
Set theory is also a formal notion. We want an informal one. Okay. Let's try some bad example. Lobster. Computer or no?
No.
Okay, an ant. Okay, a colony of ants.
Still no.
Okay, is a colony of ants smarter than an ant?
Yes.
Okay. A monkey. Why not? An orangutan specifically, let's say. Precisely.
Well, and they're comparable to human intelligence.
So, but can you think of something smarter than an orangutan? A better example of a computer than an orangutan?
And not a human, right?
It could be a human. Why not?
Like a human.
So let's say it's a human.
Oh my god.
This is the reason of the photo, okay? All right, so we have an incredibly complex system here, right? First off, it's very complicated. Fleshy, mortal, subject to impulse. There's lots of problems going on, okay? We want the computer part. We don't want anything else. So what we're going to do is perform surgery, dip it in acid until we're left with the portion that is simply the computer. So let's go piece by piece. Do you need skin to be a computer?
No.
Okay, get rid of that. Bones.
No.
Lungs.
No.
I mean, if you don't have lungs, you can't breathe. So you need some kind of like minimal life support. Someone who's dead is not a computer. So you need some minimal life support system, right? Take all the life support system, put it in a pill. And that's the life support system. What do you need for computation? What would remain for computation?
The brain?
The brain, anything else?
Peripherals.
Peripherals, like what?
Like eyes, ears.
Okay, yes, you need sensory input. Now, why do you need sensory input? And the answer is like, certainly the brain is largely responsible for computation. So the brain should come first. But we want the most general model of a computer. So a brain in a jar with no sensory input can do certain things fine. But if you have sensory input, perhaps you can do more. So it's okay to consider sensory inputs, and outputs in fact, as part of the system. We'll restore those, right? Yes?
Because also if it was a brain in a jar, you wouldn't be able to prove if it was doing computations, or would you?
I suppose not. It would not be able to demonstrate to you that it knows it is computing something. So it must be able to convince you that it does know something, right? That's a very good point. Why is the brain responsible for computation? This is an open-ended question. Yeah.
I'm not sure if I'm using this right, but the anthropic principle, where it's responsible for computation because that's how it.
I guess what I'm asking is why not the heart?
No neurons.
No neurons. But why the brain? There's a simpler answer that I'm kind of sort of leading us towards. The brain compared to all other organs we know is responsible for computation. Aristotle thought the brain was a heat sink. He thought the brain was responsible for cooling down the blood. And when you see the brain, that kind of is an easy assumption to make, but it's not true. We know today that the brain is largely responsible for all motory function, all balance, and all computation. Language even, because when you start poking around in there with a needle, people start learning their words. So as you were to separate portions of the body from persons, the ones that computation stalls is the brain. So the brain definitely, by such observations, is responsible for computation. Question? Okay. I claim that we would be left with the following. We may call it the creature. It has the brain. It has a simple input and output system of the eyes. We don't need eyes and ears. Let's just say they're eyes. You could consider ears. It's okay. But let's suppose we have just eyes. And let's also suppose further we have a single limb left that has access to some sort of manuscript or book or something, it's right. Why should we consider the input system? We want the most general definition of computation. So it's okay for us to, at least, anything that can be done with the brain can be done by this. So this is definitely a more general model of computation. It would be an agony were it not for the fact we also removed from the brain portions that are responsible for pain management and any such neurons. So it's simply left as a computer. Do we agree, were we to perform such a thing and create such a creature, that it would be a computer? Okay, we agree this is a computer. We agree that this transformation has not perturbed the act of computation. So we must agree that this is a computer, in the sense that it performs computation. Okay, now we proceed with Alan Turing's argument. Computing is normally done by writing certain symbols on paper. We may suppose that this paper is divided into squares like a child's arithmetic book. In elementary arithmetic, the two-dimensional character of the paper is sometimes used, but such use is always avoidable. And I think that it will be agreed that the two-dimensional character of the paper is no essential of computation. I assume then that the computation is carried out on a one-dimensional paper, i.e. a tape divided into squares. So the first thing Alan Turing notes is that the geometry of the writing surface, it doesn't really matter for computation. The externalization of, maybe you have some things you want to recall, you write them down. That doesn't really matter what shape the paper is. Let it be a sphere, a globe, let it be, a scroll or something. So we may simplify the model by replacing, first off, we replace the paper, which is a sequence of lines, by a one-way infinite scroll. Now, I want to emphasize, the scroll, the tape, is not really infinite, but it's arbitrarily long. The Turing machine does not have infinite memory, because at any finite step of computation, at most a finite amount of the tape can be used, right? Even if you have a machine that loops infinitely, if you pause the machine at some step and inspect it, only a finite amount of it has been written to, the tape. So at each moment, the amount of space used is finite, right? So analogously, it's not the case that we are looking at a bounded memory structure, but if you need more paper, you can always get up and go get more, right? So that's really the model, more than it being infinite. We just leave it there for simplicity. Instead of supposing it was infinite, suppose you had some tape printer that printed a new cell every time you needed one. Something like this, right? Do we agree? We agreed this was a computer, right? Do we agree that this transformation has not changed the act of computation? So you must concede that this is a computer. Okay. I shall also suppose that the number of symbols which may be printed is finite. If we were to allow an infinity of symbols, then there would be symbols differing to an arbitrarily small extent. We'll talk about that footnote in a second. The effect of this restriction of the number of symbols is not very serious. It is always possible to use sequences of symbols in the place of single symbols. Thus, an Arabic numeral such as 17 or several nines is normally treated as a single symbol. The difference from our point of view between the single and compound symbols is that the compound symbols, if they are too lengthy, cannot be observed at one glance. This is in accordance with experience. We cannot tell at a glance whether several nines and several nines are the same. Quick, are those the same number of nines? Don't shrug, you can figure it out.
On the left is one longer.
How'd you do it?
By threes.
You did by threes. So you said 3, 6, 9, 12, 15, 16. Okay, 3, 6, 9, 12, 18. Maybe I made a mistake. But anyway, I couldn't look at a single glance. You cannot do an arbitrarily long computation. The sentence here, this is in accordance with experience, is incredibly important. This is, again, his correspondence to the intuitive definition. It's the fact that the Turing machine must take atomic steps because when we compute, we also must take such atomic steps. It is impossible to do an arbitrarily large problem at an immediate glance, within a single step. So in order for a Turing machine to do such a thing, it must take a sequence of steps. Because we also must take a sequence of steps. This is, in fact, incredibly important. The other thing he asserts here is that it is sufficient that our tape alphabet and our input alphabet all be finite. The question that I think we all had on lecture 1 when we were talking about DFAs is, what happens if we allowed infinitely many symbols? what he says here, it's not very serious. It's not important. Anything you can do with infinitely many symbols, you can just do with finitely many just by using a sequence of symbols, right? We don't need infinitely many letters because you build other complex ideas from sequences of letters. Words are made from letters and sentences from words and so on. But they're all from an atomic finite alphabet. Questions?
I have a small question. So the immediate implication of an infinite alphabet is that a DFA will have infinite states.
Great question. If you have to formally define the transition function as being total, I suppose.
Yeah, but our brain is not infinite.
Yes.
So our Q set is limited, right? Does that limit the amount of computation we can do?
So to separate two parts of the argument, the first argument he makes here is that you cannot do less with a finite alphabet. It's not the case that the finite alphabet is weaker. The second argument he'll make in this footnote is that you cannot do more. So let's see where I put this. So here's the footnote. If we regard a symbol as literally printed on a square, we may suppose the square is x and y coordinates 0 to 1. The symbol is defined as the set of points in the square, viz. The set occupied by printer's ink. If these sets are restricted to be measurable, we can define the distance between two symbols as the cost of transforming one symbol to the other, as the transforming one symbol into the other if the cost of moving unit area of printer's ink unit distance is unity, and there is an infinite supply of ink at x equals 2, y 0. With this topology, the symbols form a conditionally compact space. We're talking in the language of topology here, which I don't expect many people to know, but anyone know what topology? You know topology? I know Caleb knows topology. Caleb knows topology. Do you know what the definition of a compact space is in topology? Okay. Topology is a set of sets with some properties. And so first off, suppose we have a set of symbols. Just consider anything you could draw. Suppose the set was infinite. And let's suppose we're considering any possible combination, a symbol to be just any possible subset of this unit Cartesian plane. Any possible set is the symbol, right? By the restriction of measurable here is a formal definition, but the precise definition is a little cumbersome, and it was invented to discuss integrating over something to compute the area under a curve, but there are many functions that are piecewise and weird that you can't compute the area under. For example, a symbol that would be not measurable was, let's suppose you place an imperceptibly small dot of ink at every rational. Okay? That symbol would appear by an imperceptibly light shade of gray. Because there would be all these irrationals and there'd be little rationals, right? So like, that would not be, we would not consider that to be measurable. A set is said to be measurable if it has volume. So if the shape has area, if you can look at it and be like, yeah, I can calculate the area of that probably. Even if it's a fractal or something, you can say like, okay, that's a measurable symbol. Okay, done. So suppose we only restrict ourselves to the measurable symbols. The definition of a compact space is every open cover has a finite subcover. So what that means is if you have an infinite set of sets that union over to cover all possible symbols, you can choose finitely many of them, or really they will partition themselves into finitely many classes. They're not really equivalence classes, but they'll fall into distinct regions and only finitely many of them. So if there were infinitely many symbols, essentially what he's saying here in the language of topology is that up to the distinguishing factor of the human eye, there would only really be like finitely many you could tell apart, right? Too many of them would be arbitrarily close, and you wouldn't be able to say that there's a big difference with them. So compared to the previous argument, he says, given finitely many symbols, it's not the case you can do less. What he's saying here is like, given infinitely many symbols, it's not the case you can do more. Because the infinitely many symbols will fall into nice little categories of distinctness up to like handwriting perturbation and so on. It is even the case there are distinct symbols that we agree mean the same thing. For example, there's two ways to write the letter A, right? Distinct symbols, same meaning, right? So in both cases, we know that the alphabet is finite. Two things. Finite work is done in finite time. This will be later important for the development of complexity theory, algorithms, and so on, the actual analysis of algorithms. Here we're just concerned with the definition of algorithm. And the number of symbols of necessary for computation must be finite. So sigma is not infinite. First question, first problem solved. The behavior of the computer at any moment is determined by the symbols which he is observing and his state of mind at that moment. By the way, this is the etymological root of the term state in computer science. We don't call the states of a DFA, we don't call them vertices or nodes or anything. We call them states because they're shorthand for states of mind. We may suppose that there is a bound, capital B, to the number of symbols or squares which the computer can observe at one moment. If he wishes to observe more, he must use successive observations. The new observed squares must be immediately recognizable by the computer. I think it is reasonable to suppose that they can only be squares whose distance from the closest of the immediately previously observed squares does not exceed a certain fixed amount. Let us say each of the new observed squares is within L squares of an immediately previously observed square. So what he's saying here is, although the tape is large and in charge or whatever, that only B of them can be read to at a certain moment. Let's say B of them are read. So he's only looking at a small local portion of the tape. Then the tape also only can move, you move the tape head only like 3 squares or whatever, right? So you don't jump halfway through you don't jump a million cells away. You can only move a few cells from where you began. Both of these are in accordance with experience, and he makes these generalizations. And our definition of the Turing machine, we set edit L and B to be what?
The alphabet?
No, L and B is the bound of the number of squares that are read at one moment. B is the number of symbols that can be read at a single moment. L is the number of squares you can move at a single moment.
1.
Yeah, L and B are both 1. You read a single symbol, and you can move at most 1 symbol away. But it doesn't matter if these were like 3 or 7, it turns out. Right? So we set L and B to be 1, and we also have defined the codomain, the domain here, right? The only thing that is necessary for us to condition on where to move is the current state, state of mind, and the symbol that we're reading, right? The behavior of the computer at any moment is determined by the symbols which he is observing and his state of mind at that moment. That tells us that what determines that comes next must be the current state of mind, the symbol read. So we have defined the domain of our transition function as this. That's what he's saying. We'll define the codomain in a second. Now again, you agreed that this thing was a computer. Do you agree we've now replaced the eyes and the hand with a paper clip and some sort of sensor? Maybe, so let's suppose there's like ferromagnetic fluid on the tape and that it injects nutrients when there's a 1 or a 0 on the tape, something like this, right? So now this is a non-trivial and harder to imagine change, but would you agree that it could be implemented in such a way to not perturb the active computation? So do you agree that this change does not change computation? If you agree this is a computer, then you must agree this is a computer. Okay. We will also suppose that the number of states of mind which need to be taken into account is finite. The reasons for this are of the same character as those which restrict the number of symbols. If we admitted an infinity of states of mind, some of them will be arbitrarily close and will be confused. So first he's saying the states of mind that need to be considered, not necessarily of the brain, but of any specific algorithm, must be finite. The states of mind is finite. Second, if there was infinity, that means they're too close together, they'll be confused. It's okay to just do finitely many states, right? Early on in the paper, he mentions that human memory is necessarily limited. So this is okay as well, right? The states themselves are limited, but the tape can be arbitrary. So you're juggling a few portions here, and the rest can go on the tape. Maybe it's 1,000 states, who knows? But it's certainly finitely many, right? So we know that Q is finite, whatever it happens to be, per specific algorithm. Let us imagine the operations performed by the computer to be split up into simple operations, which are so elementary that it is not easy to imagine them further divided. Every such operation consists of some change of the physical system consisting of the computer and his tape. We know the state of the system if we know the sequence of symbols on the tape. Which of these are observed by the computer, possibly with a special order, and the state of mind of the computer. We may suppose that in a simple operation, not more than one symbol is altered. Any other changes can be split up into simple changes of this kind. The situation in regard to the squares whose symbols may be altered in this way is the same as with regards to the observed squares. We may therefore, without loss of generality, assume the changes to the squares whose symbols are changed are always observed squares. Essentially what he's saying is like, you write where you're reading. Now if you're reading somewhere else and you're writing somewhere else, who cares? You read what you're writing. Tape head, right? Now if these squares are marked only by single symbols, there can only be a finite number of them, and we should not upset our theory by adjoining these marked squares to the observed squares. If, on the other hand, they are marked by a sequence of symbols, we cannot regard the process of recognition as a simple process. This is a fundamental point and should be illustrated. In most mathematical papers, the equations and theorems are numbered. Normally, the numbers do not go beyond, say, 1,000. It is therefore possible to recognize the theorem at a glance by its number. But if the paper was very long, we might read theorem something, and then further on in the paper, we might find hence applying theorem something. In order to make sure it was the relevant theorem, we should have to compare the two numbers, figure by figure, possibly taking out figures in pencil to make sure they're not being counted twice. And if in spite of it, ignore that. Suppose we want to determine these two numbers are equal, symbol by symbol. We did a Turing machine for WW. And the way we went so is we marked 1, we checked 1. We went back here, we marked 5, we checked 5. We marked 7, we checked 7. Now if you were to do 3 at a time or 1 at a time, it doesn't really matter. But we did so pencil, right? We could perhaps, by a pumping argument, create a number larger than any finite human memory, but you could not do this in the brain necessarily, but you could definitely do it on the tape in a mechanical way that just goes symbol by symbol in a very dumb manner. But it could be done by a human, right? So what he's saying here, it's okay if gamma can be adjoined by many other symbols, right? Suppose we, instead of putting an X, we did this A dot. And A dot here is to represent a marked symbol. And what A dot does is it's as if it's this distinct, completely different symbol, okay? But it means, it has a semantic meaning of like, we marked that symbol. So it's as if we read W hash W, we're going back and forth marking stuff. But instead of marking, we read A, write A dot, which by the way, A dot, again, different symbol. But it's analogous to striking through it, right? So it's okay, what he's saying here if gamma is some other set of symbols that include the input symbols, but something else that maybe helps with computation. That's okay. That's all he's really saying here. The simple operations must therefore include changes of the symbol on one of the observed squares, so you can write. Changes of one of the squares observed to another square within L squares of one of the previously observed squares, so you can move. It may be that some of these changes necessarily involve a change of state of mind. The most general single operation must therefore be taken to be one of the following. You either a possible change of A, of symbol, together with a possible change of state of mind, or a possible change of observed squares with a possible change of state of mind. So what he's saying is you can change state, but you can also change the symbol that you're writing and the position of the tape head. So let's just group all these together in one possible thing. So you change the state, you change the symbol on the tape, and you move the tape head left or right. So we can combine this to get the codomain of our function. Q, gamma, LR. You change the state of mind, you change the symbol on the tape, you write, and then you move left or right. So here all he's explaining is what the codomain is. And again, this is a modern notation. Turing's definition of the Turing machine is a little cumbersome. We're just trying to explain why ours is through him, right? We may now construct a machine to do the work of this computer. To each state of mind, the computer corresponds an M configuration of the machine. The machine scans B squares corresponding to the B squares observed by the computer. In any move, the machine can change a symbol on a scanned square, or it can change any of the scanned squares to another square distant not more than L squares from one of the other scanned squares. The move which is done in the succeeding configuration are determined by the scanned symbol and the M configuration. The machines just described do not differ very essentially from computing machines as defined in section 2, and corresponding to any machine of this type, a computing machine can be constructed to compute the same sequence, that is, the sequence computed by the computer. So here's this concluding paragraph, and we began with, what we're doing here is we've now replaced the matter of the brain with a transition function with our appropriate domain and codomain, and a finite set of states. Here there's 3, but perhaps there's 1,000, who cares? We can replace the matter, the final fleshy, intuitive portion, by a very formal notion, one that's fully defined in any system. And here you all agreed that this was a model of computation. Do you agree that this perturbation does not change the model of computation, the act of computation? So we must agree then that the Turing machine is intuitively capturing the definition of what is a computer. That's the Turing machine. Let's phrase everything back again, right? We composed all these constructions and we were left with the Turing machine. This is the direct appeal to intuition. And this is why Alan Turing really was such a genius for his time. It's not the fact that he defined what a computer was, but the fact that he defined a model of computation that had a sufficient explanation about why it was a good definition of a computer. So many other people defined things that accidentally were what we would call Turing complete. They're accidentally equivalent to the Turing machine, but they had no idea. They're just coming up with stuff. They're making stuff up. The lambda calculi, the recursive functions, they had no idea. They just keep taking something, you keep generalizing, it's going to eventually be Turing complete, you know? But here, he started the other way, and that's what we give him the credit for. Yeah. So, let's rephrase everything in our argument. Let the arrow denote there's a simulation of one on the other, okay? Why, for each of these models of computation, does there exist a simulation of it on the human mind?
The human mind can go in and directly simulate each one.
Yeah, these are all fathomable. You don't know these, but let's suppose they're all fathomable. Each of these can be simulated on the human mind. You walk through them step by step. Done. So we know each of these can be simulated on the human mind. We also know that by Church's thesis, there exist simulations of any of these reasonable procedures. And in fact, you can prove these. It's not too difficult to find the actual simulation of one on the other. The same way we did an NFA and a DFA and a DFA and the NFA. These arguments exist. What Turing brings in here is he solves the question that we're trying to ask, which is that the human mind can be, quote unquote, simulated on a Turing machine, at least with respect to computation. So that's sufficient to prove that all of these then are equivalent to the human mind by composition. All of these can be simulated on the human mind, but then the computation that can be done by the human can be simulated on a Turing machine. So we get our if and only if, we get both arrows going both ways. And we have a sufficient argument that all these models of computation end up being equivalent. Church's thesis can be said as any reasonable, fathomable model of computation is equivalent to a Turing machine. Turing's thesis could be said as the Turing machine is equivalent in power to the human mind. And then we combine these to get the definition of algorithm is independent of any specific formalism. As long as your definition is not a DFA or a PDA, it's probably equivalent to a Turing machine. These are all good models, they're all useful. That's basically what the combination is here. So again, we had two arguments. I'm going to quickly go through the second one. We proved that Turing machines are equivalent in power to the human mind by doing this if and only if double set containment. The second point is we want to demonstrate that there is no computing device strictly more powerful than the human mind. This is going to be difficult to argue because, of course, we're working within our own limitations. The question we want to ask is, why is there no NFA, CFG, L human is this large and robust class we know is equivalent to the Turing machines. Why is it the case that there's nothing over here? We want to just basically assert that there is no automaton that can go there. At least none that we would care about. So let's back up a little bit. Recall the fathomability criterion. If C is fathomable, then L can be simulated on L human, right? What is the contrapositive of this?
See if C is not fathomable.
That'd be the converse, I don't remember.
Yeah.
You have to you flip it and then you take the negation. So what's the negation of this? In set theory it's complicated, but let's take the simple one.
So if it's not human, then it's not fathomable.
Basically, there's some hand waving there, but basically, and it's not necessarily true that if one's not a subset of the other, that the other must be a strict subset of it. But suppose we had something that was a strict subset of it, right? Something that is strictly stronger than the human mind with respect to computation. It's definitely a negation of that. That's definitely false. But it must imply that if we have the fathomability criterion, if the whole reason that the first proof worked at all, it must be the case that C is an unfathomable object. In the sense that, given a description of the machine, you cannot run through the steps of it on your mind to produce an output. Otherwise, of course, the fathomability would, of course, give you the simulation on L human. In fact, is there an automaton that is strictly stronger than the Turing machine and the human that is unfathomable? We've actually seen one already. There is one automaton that you cannot walk through step by step in your mind. It was the DIA from homework 1. On homework 1, I defined a DIA, and I told you to prove that it can decide every language. Every single possible language is decidable by a DIA. Why does it not satisfy the fathomability criterion?
You can't have infinite states.
Yeah, you have, the description of a DIA is infinite in length. In some sense, if it's fathomable, another thing we can extend as a corollary is that a description of the machine must be finite in length, right? You cannot have an infinitely long C program. You cannot have an infinitely long program. This doesn't make any sense. You would have to look through the infinite list of if statements. You would never reach the end of it. So how do you know if your input is in one of these if statements? It doesn't work. So for boring reasons, in fact, it doesn't satisfy the fathomability criterion. And we also know that it is strictly stronger than L-human because it can decide every language. Are there things Turing machines can't do? We'll have to see. We'll spend several lectures on that. But the answer is yes, in fact. The argument really can never be completed. How can we argue that something cannot be, how can we argue that we can't think about something? That's sort of an argument, by necessity, this is something we can never complete. There are all kinds of things people assign fancy words to, like new Mysterianism, and all they say really is like any sufficient explanation of consciousness or something will always be incomplete. You can never finish the job. You can never sufficiently explain anything like this. And were we able to explain something that was fully unfathomable, then certainly like it would be fathomable in some sense. Maybe not in a direct computational way, but at least understanding it would perhaps lead to, there would be a connection there to us being able to simulate it, right? So by the fact that we exist in such a class, we cannot ever talk about anything greater. Sort of the DFA has no idea what the DFA has no idea what a PDA is, and so on. It has no idea what it's talking about, right? So the Church-Turing thesis, this is not a fully philosophical black box, you put it away kind of thing. It's very applicable. You'll use this throughout the course. There are a few immediate applications. Well-specified pseudocode can always be implemented. You don't have to actually write code. You can just think about it. So by the Church-Turing thesis, if you think you can write a Turing machine for something, then you can. You don't have to actually write the Turing machine. Does there exist a Turing machine that can compute multiplication of binary numbers? Why?
So I can think of what it would do.
Yeah, we can multiply binary numbers. By the reduction, essentially, that Turing did, the distillation, there must exist a Turing machine because we take that process that we would do with pen and paper, we can convert that to a Turing machine. Now, we don't know how many states it has, we don't actually know what the Turing machine looks like, but that's okay because we know it exists. Non-constructive in some sense, but it's there. So you just have to think about the algorithm, and then it exists. Here's an immediately interesting thing, is that this is not true for PDAs or DFAs, but we have something called a universal Turing machine. The universal Turing machine is a computes the computable function. Every Turing machine computes a fixed function, right? They're fixed. But we can have a Turing machine compute the fixed function, which is the simulation of the machine on the input. So this is a computable function which takes as input a machine, a string description of a machine, the code, a word, and it outputs if that machine accepts the W. Why does the universal Turing machine exist? Because we can take a Turing machine and simulate its transition function on its input. So because we can do that, there exists a Turing machine that takes as input another Turing machine and simulates that Turing machine. There is a universal Turing machine. Now we can actually program the Turing machine. We know how to do this. It's actually not super complicated. It's just quite tedious. But we can fathom that the universal Turing machine exists without having to actually program it. It exists. Ooh, I don't want to write the code, but we know it exists. Now it does compute a fixed function, which is in fact like a universal function of the output of whatever that machine was going to output. The way it actually works is it was like, okay, it reads the transition function of M, which is written on its tape, U's gonna say, oh, delta's gonna do that, I'm gonna go over here to the tape over here, and I'm gonna change something, and I'm gonna go back and see, what does the transition function do next? Then I'm gonna go over here, and I'm like, okay, I'm gonna read the 1, write a 0. It's gonna go back and forth. Turing machines can simulate each other, and that's not true for any other automaton. So we get something that nothing else, the PDAs and CFGs and NFAs and nothing else has, is this universality. And that follows immediately from the philosophical argument. It can also follow from the construction of the universal Turing machine, but here we get it for free. Finally, any results about the formal model, which is the Turing machine, must implicate the intuitive notion, the algorithm. So this is really the power and the point of this class, is we are allowed to say things about the intuitive notion because we have a correspondence between the intuitive and the formal, the scientific and the pre-scientific. We cannot prove things about the intuitive and the informal, ever. We can't ever prove anything about 3 bananas, but you can prove things about 3. So you work with the 3, the formal ideal concept, and then you can apply that back to the special case of if you had 3 bananas. It's the same thing here. You can prove theorems about Turing machines, and any of those theorems must implicate the informal notion, the intuitive one. So, for example, we gave pumping lemma arguments for DFAs and NFAs. We gave pumping arguments for PDAs. We can prove that there are languages that do not have Turing machines to decide them. There are such problems that are undecidable, as we'll call them, to Turing machines. And what that implies, in the implication there, is that no human can equivalently solve such a problem as well. So there are things that we cannot do. And we can find such a limitation through the Church-Turing thesis. Now again, that limitation is conditional on the Church-Turing thesis. And it's only true if the Church-Turing thesis is true. But we gave as close to a proof as we could of the Church-Turing thesis, so you should believe it to be true. And you should believe such a condition. Questions? Yes?
Does time come into a factor here in sort of thinking about this, or?
Yes. So we did give a Turing machine that took like quadratic time that you and I could probably do in linear time. And the answer is, in the context of this unit, we're not determined about efficiency yet. We're only determined about possibility. So even if there exists a slow Turing machine for a problem, we're happy there exists a Turing machine at all. That's what we're concerned with. Whether it's the fastest one, we don't care yet. We'll care after the unit in like months from now. When we talk about that. There's something that's important with respect to the argument that we've made that I haven't heard anyone talk about yet. There's a small concern with the Church-Turing thesis, particularly with Turing's argument. And usually people, especially Intel thread people, take problem with Turing's thesis. But does anyone have such an objection? Yes.
Would it be that, is it related to time as well?
No.
Okay.
Sorry.
I have an idea, but I don't know if it's what you're trying to ask.
Okay.
How about coming up with a random number? Is that counted as computation?
Philosophical discussions about randomness. It's important to know the definition of a Turing machine is definitely deterministic. Randomized algorithms, the way you model randomized algorithms is that the randomization is done externally. You give the machine a coin, and that's how it gets its randomness.
I see. But my brain is truly random, though.
Is it?
Neuron impulses and.
Is the universe, is it not governed by deterministic laws of physics? Fully?
Well, we have quantum mechanics.
But isn't such a macro scale event as determining or guessing a random number? I bet you right now I asked you for a random number.
Perhaps.
Give me a random number between 1 and 10.
7.
And you were going to say 7.
Yes.
It's predetermined.
It's.
Okay.
How did you know he was going to say 7?
I was also going to guess 7. The 7 is the most common number, so it's in fact not random. That's not exactly, that's an important discussion, but it's not the discussion I was kind of hoping someone would object to.
What's your.
Learning.
Oh, yes.
The transition function is fixed, right? So like, how is this thing gonna, this is a fixed sequence of states. The definition of algorithm is fixed, it's code. It doesn't allow itself to update, it doesn't allow us to learn from mistakes, and it doesn't allow itself to make any changes to itself. But this isn't a problem.
Can I just put what I learned on the tape?
Yeah. So I guess here's the sentence. Yes, learning exists, and we allow ourselves to learn from mistakes, but the Turing machine is fully deterministic, and the algorithm itself does not change. But in learning, the rules that govern how learning occurs are themselves deterministic. So that's not the algorithm, the neural net or whatever, that's not the algorithm. The algorithm is what operates on the neural net, which would be in context written on the tape somewhere. So the interaction with the net itself would be deterministic. And if that's not deterministic, then you go up a level and that interaction with that thing would be deterministic. It turtles all the way down. It's always going to be deterministic. That's an objection I think most people would see and bring up. The idea of learning. Yes?
Is that like that you can, the fact that you can simulate learning?
Deterministically?
Yeah, or
Yeah.
then it's, yeah.
Precisely, yes. The Turing machine is not the actual algorithm, but it's in that case it would be the algorithm to create the algorithm. That would be the deterministic part. And you can back up eventually, you'll always hit something deterministic.
And that's a universal Turing machine, or?
The universal Turing machine is simply the ability of one Turing machine to simulate another. In that case, it would need to be necessarily true that the neural net thing is like equivalent to the Turing machine, when it could be something specific. For example, you could have a Turing machine simulate a DFA without having the DFA hard-coded in the states. It could be the description of the DFA written on the tape. The Turing machine can simulate it both with hard-coded states and with it written on the tape. You could have a universal DFA simulator, because given a word in a DFA, you can run the DFA on the word. So you can have a universal, a DFA simulator as a Turing machine, technically. Right? More questions?
So when you say we have finite state, it's technically, we technically have access to infinite states. It's just on the tape.
But at any fixed moment, at most a finite amount of the tape has been used.
Yeah, because we have finite time,
Yes.
right? But it doesn't mean that the tape is finite.
The use of the tape is finite, even though the tape is not finite.
Given finite time.
Yes. And we only consider, the definition of an algorithm is again one that must halt to output an answer. So if it halts, it outputs in a finite number of steps. So it must use almost a finite amount of the tape. So any use of the tape is arbitrary, but not infinite. And there is a huge distinction we will make more explicit between infinity itself, in a literal sense, and a limit towards infinity, in a procedural and arbitrary sense. Those two notions are very distinct, it turns out, and we'll have lectures on why. More questions? All right.